guess now that I'm doing that, it doesn't matter all that much that whether I record or not, because the classes occur at the same time as they would on site. But I'll record them anyway, because I said I would. So anyway, we're going to miss, I guess we missed a couple minutes, but not a huge deal. Just sort of going over, for those of you that just joined us, we're sort of going over this abstract hash map idea, which is going to be an abstract class that gets implemented and extended by a concrete version of the hash map, which means things like bucket get, bucket remove, which is part of the get and the remove. The determination of how to do those are left up to whoever is extending this. And so we were about to get into here collision handling and what happens when, for example, you put something that's already been put. So that's these four methods here are going to be implemented by whoever goes and extends the abstract hash map. So first, to talk about how we're going to do that, we first need to talk about collision handling, sort of where I left off last time. Collisions are going to occur anytime you've got the same key going to multiple values. So here we have the key 1 going to this value, but then someone put 2 values in for key 4. This was the first one inserted, and this one was the second. With separate chaining, it's called. This is one method. So the question is, how do you resolve this? So the question is, how is this resolved? Well, first method is separate chaining, it's called. This basically says each cell in the table is going to point to a linked list of entries. So this this here would be a linked list, and it would keep going. So if you had another key 4 that came in with a different value, that would be position 3. This means we have memory outside of the table because we have to create this linked list in of itself. It's also a very simplistic approach because there might, frankly, be a better way of organizing that data. But we'll take a look at it anyway because it's a very popular way of doing it because it's very simple. What we're basically going to see is that, so like your bucket get, your bucket put that we saw before, we'll have a delegate operation to this list-based map at each of the cells. So for example, when you do your get, you get a of h of k dot get of k. Where the index to that is dependent on the hash of it. So h of k is going to be hashed, which is going to return a separate value. And then if you do a put, it's a of h of k dot put k of v and v. And then you increment n, because inside of the put implementation for this, you'll use n to determine where in the linked list you want to insert it. So this determines the new item goes. So that's why we're updating n in that case, because basically it would go, the first one would go in position 1, we'd increment n to n plus 1, so it would go in position 2, for example, and so on and so forth. Now what that looks like a little bit in a little bit more detail, that's kind of the vague high level structure of those functions. Here we're now finally doing something real. We're doing a concrete class chain hash map, extends abstract hash map. And it's going to have a unsorted table map with our key and value pairs in our table. So when we say bucket get, first we get the bucket and we return table at H. So that's literally just returning the in our array of key value pairs, which is unsorted. We're literally just returning table at that hashed value. Notice that we have int h here. That's the hash value. So we can do a bucket get. Let's see if they've got this on the next page. Well, bucket get, remember that's called from before when we do our get. That calls bucket get of hash value, key. So hash value of key, it's assumed that that's going to be implemented inside of this guy. So you already have the hash value, and then once you have the hash value, again, you're just going into an array and you're getting that position. Because remember, all that a hash table really is just an array of values. So don't let that confuse you, because when we say bucket equals table of H, bucket is there's a bucket per entry in this structure. We've got basically this array of all of these buckets. Each one of these goes to, they're calling it a bucket, basically, which is a linked list. So we've got one item here going to another item. If another item comes in, we'll put it up here and we'll send it to the next item. So on and so forth. That's our bucket, and each of these has a similar bucket with stuff in it. This has a bucket. This one has a bucket. They all have buckets. So that's why we say, when we say table H, this is the hash value. These are the hash values. Those are the H's that we're going to get. So we get the tabled hash value, and then we get the bucket. Then we have to call bucket get of K. So this is where that thing I was just showing you comes in finally. Where was I showing you that? Was with get. This is an abstract version of it because it says A of H of K get. Well, we've already gotten H of K, so now we can just do A get of K. And that's just a linked list traversal at that point. So I'm going to write that down in here. So that is a linked list traversal to get K out of bucket. So that is literally like you got the bucket you got was maybe this thing. Maybe you got this bucket, and now you have to get that value out. So that's how that works. So let me know if there's any questions about that. It's a little bit, the thing about hash maps is, first you got to understand that we're storing a unique position per hashed value. But then you get into this thing called collision handling and chaining. It becomes a little more confusing because you're kind of layering one, you're using another data structure, namely a linked list or something like that, a linked list in the case of chaining, to store your actual items. Now a bucket put, this is where we say the size of n has to increase, because basically when we do a put, n is the size of the number of things in our bucket. When we do a put, we get back the key that's associated with that value, and then we got to increment the number of things in that bucket. So we're doing the reverse of what we do in a get. We just put it in instead of just simply getting it out. Bucket remove, again, gets that bucket. But now remove k, instead of doing a put, we're going to go through that linked list and we're going to look for that k and we're going to take it out. Now remember what I mentioned before about the fact that, well, if we've got this linked list, and I showed you that, that crude picture I just drew here. Where was it? Here. So this is our structure. We've got this list. This is an array. But each array has a bunch of stuff in it. So this is going to have a bunch of stuff. Each of these could have, like, 3, 4, 5 items in them. So now, what if we want to print all those? Well, that's where iterable comes in. Iterable basically says we're going to store these in an array list. Going to go through and get the bucket at each of them, and that's why it's an embedded for loop here. It's going through all the buckets. For each bucket that we get, we set that we create an entry for the table, which is here, and then we add that to the array list. So we end up with an array list version of what's in the table. So sort of switching topics a little bit, as I said, feel free to chime in here if there's any questions about, because that's sort of the core content, is the hash table with the chaining. Now we go on to linear probing. With linear probing, this is a different methodology for resolving collisions. It's a slightly more elegant approach in that we don't require, and actually they don't say that here, so I'm going to list some things about this. This is a different method for resolving conflicts, but doesn't require outside data structures. What I mean by that is, before we had to have these buckets, and the buckets were linked lists, and we had to go through all of them. Well, that's the simple way to do it. Linear probing is slightly more complex, because what happens is, let's say we get a bunch of keys in here, and we've got, for example, an hash function that's just, you take whatever and you mod 13 on it. So we've got 18 going in, 41 going in because the mod results of that are 2, 22 going in, mod results of that are 9, 44 going in, mod results of that are 6, 59 going in, mod results of that are 7, 32, 31, 74 in that order. Now, if you end up having an overlap, like this next one is going to be on 44, then you have to put it in the next cell. So, for example, here they're showing that we've got key 44 going in, and we end up in position 6. Well, the modulus results of that are actually 5, but we had to go into 6 because 5 was already used. So 44 goes in. I'm not sure about the rest of these, but that's definitely one that goes into the next position. So instead of using this one, we take it up and we put in the next one. That's essentially what a linear probe does, and we call it a linear probe because you probe for the cell that you're about to put in. So x mod 13. So we do 44 mod 13 and 18, and we get 5. But when we do 44 mod 13, we get 5. We probe that cell. We probe the 18, the cell that has 18. We see that something's there. It's going to lump together that by putting it in the next one, and that's basically why we call it a linear probe. So if we consider, say we start at the cell that's got that hash value, that's what we're saying we start at. So in the previous case, when we're putting 44 in, we would start at 5. And then we probe consecutive locations until an item with that exact value is found, or we find an empty cell. Find an empty cell, we put it there. So we go one at a time, and that's why it's called linear probing, because we're going one at a time through the cells to find an empty location. For handling insertions and deletions, so when we do a remove, we have to search for that entry with that key value. Now, ask yourself for a second, well, why are they doing this? Why are they saying, okay, so you got to put defunct or some sort of null value of some sort, some special value in that position? That is because essentially this defunct is going to say that if someone else goes into that position, they can actually use that position, right? So that's why we do that, so that you can actually reuse that position again. Now you might be saying to yourselves, well, why don't we just null it out? You could. If you just null it out, you can then reuse it. And I've seen implementations that do that. It all depends on your implementation. It all depends on how you want to do it, because in a lot of times, if you've got a bunch of things clumped together, you might want to maintain that chain. And if you just null it out, that sort of breaks the chain. Now when we do a put, as you see, it's also looking for defunct. So either it's empty or it's looking for defunct, and then you store it when you're doing your update, when you're doing your put. Now, the probe hash map in Java is another extension of abstract hash map. Remember, what you're trying to do here is you implement bucket get, bucket put, bucket remove. And so it's going to extend abstract hash map and implement those. So we've got a find slot helper function that returns an index with a key or the next available. So we've got a do while loop here that's basically going through and finding the first available position to put that new item in. Bucket get uses find slot as well because it has to find the first one that's there and return it. Bucket put has to find it to put it in there. This one here, just to cover this, so find slot finds our J position. And then we do table J set value. Then we convert this to a proper index, so we say J plus 1 converts to the new map entry of that K and V value. All this does is that table J, remember that table J set value is just an element basically. So it has to set the value to that V. But here is the actual index position of it, and we insert the new map entry for it right there. Bucket remove, we do a find slot, we get the value back, and then we set table J to defunct, and then we subtract 1 from N to back it up. A third method of resolving collisions is called double hashing. So double hashing uses this thing called D, which is our next hash resolution value or function. And I'll let you take a look at some of this stuff. I didn't want to get too deep into double hashing, but basically you're just creating a new hash value. For example, I plus JD of K mod N. So it's a slightly different hash value. Here you would choose your I values. For example, your H is your hash, so that might be K mod 13. But then your secondary hash, if there's a collision, you would go to your secondary hash. So if there's a collision, you go here. To figure out what the next spot is that you insert into the hash map. So now finally, talking a little bit about performance of hashing. Worst case is that there's always going to be collisions. But this is where we get into theory versus practice. So in theory, yes, it's O of n because we have to say, worst case, O of n, because we have to say that there could always be collisions. But you're not really going to get that ever unless you have a very primitive, very junky hash. Furthermore, what you can do with proofs and mathematics and proving this stuff out is you can show that the expected number of probes is going to be 1 divided by 1 minus some alpha value. So you can essentially show that you're not going to have O of n time. If you're using truly random numbers or something random about your hash, you're going to have a much smaller percentage of the time that you're actually having collisions. So the expected runtime of dictionary ADT operations is O of 1, which is the good part about it. This is the reason people use hash maps, because it's O of 1 for pretty much everything you're going to do. You do a get, you have to hash that value, and then you get it. I mean, you just get it. You do a put, you hash that value, you just put it there. It's O of 1. So a lot of people use this for a lot of things because it's very fast. So at the end of the day, that's why we use that. All right, so think about if you got any questions while I'm loading up. I'm going to load up the next set of slides, which is sets, and that's the last thing we're going to look at for this week. So go on and we'll look at sets here. I'm not finding it for some reason again. Oh, darn it. Where in the world did it go? Okay, there it is. It's on the desktop, of course. So now that you understand, or hopefully have a good understanding of hash maps and maps, multi-maps, all the stuff we've talked about this week, sets and multi-maps shouldn't be too hard to extrapolate out what we're doing. In fact, it's simpler in some ways, in many ways. As we know from math, set is just an unordered collection of elements. You just indicate membership in the set. So, if you've got 7, 13, 5, you can say that those are all members of a set, right? The only difference with multi-set is you can contain duplicates. So you could have 2 7s, a 5 and a 13 or something. And we've covered multi-map already. So that's just a traditional map, except with multiple keys possible. Set ADT is very simple. You've got your add, your remove, your contains, your iterator. So adding just puts it in the set. Again, there's no value. It's just a key that's going in this set. Remove is removing that key. Contains tells you membership. Is that value, or is that key rather, in the set? So we also usually, in a set ADT, we also use the idea of union and intersection and subtraction to be consistent with what the mathematical definitions of a set are. So when you do a union of S and T, for example, either E is in S or E is in T, and that union returns a new set that has the results of those operations in it. So for each one, it's going to say it's either in S or it's in T. Same with intersection, except it basically says it's in S, but it's not in T. So these are just standard mathematical definitions. Same for subtract, it's just the standard math definition. There's a few helper functions that we have called add all, add retain all. Add all, for example, would take all of the existing keys in T and put them in S. So those are essentially just renamings of the union intersection and subtraction. Add all, retain all, and remove all. Just sort of simplified names for those. So we can store a set in a list, would be one implementation of it, using space O of n. So we got tiger, bird, frog, horse. Each of those is just a unique, in this case, a unique key that's going in the list, and that's our set, basically. So here we see that we've got a generalized merge where basically we say that, okay, if we want to merge two sets together, this is how we would go about doing it. So if the element A is less than B, we would remove A at first, so we take that out and we put it back in. These auxiliary methods A is less actually are responsible for putting that back into the merged list. And what you can do is you can use these generic merge operations to perform your intersection and your unions. And in a list situation, these are all going to run in linear time because it's a O of n situation. I think that, yeah, this stuff we sort of talked about before, just by virtue of the fact that I'm covering sets last here. Multimap was, I mentioned before, was basically just a map that has multiple keys in it. And this is a hash multimap, which is what we just got done covering in the previous set of slides. Slightly different implementation of it, though, so if you want to use these slides for your own purposes, you could do that, because this just simply, the big difference here is the hash multimap is a list implementation of it, and it doesn't have the abstract hierarchy that the previous one did. So we basically just have a new hash map created here, which is just a map from that previous lecture from last time, and then we just do our put this is similar to what I talked about at the beginning of lecture today, where basically you kind of have buckets. Like this is a new array list that's going to be attached onto the location of each of the keys in the map, and then you would would put that in there. And then we of course also have an iterable list that returns back, because of the fact that we've got all these array lists in each of these map positions. It has to concatenate that together, send it back as a list, and then you can actually print it. Alright, so that's it for today pretty much. I usually like to keep these videos under half an hour, but we had quite a bit to cover. I just wanted to log in again and remind everyone. It looked like we had a few people that joined late, which is no problem, but just wanted to remind everyone what's going on with the lab. So if you go to D2L, there is now a lab on there, lab 10. And I'll be putting this up as part 3 lecture. But anyway, 10.33, 10.34, they'll be due Friday as normal. I've already got a handful of people that have submitted, but if you haven't yet, then you'll want to do that. And yeah, so that's it. I will be making an announcement sometime by the end of the week about what's going on next week. We will be having class next week, but we will not be having Monday class. We'll be having Wednesday class. I'll be having, for my Tuesday class, I'll have that, my Thursday class, my Friday class. But Monday is the big day for brain surgery for my son. So that's a really important day, and I can't even do online lecture on that day because I'll be literally by his bedside while they're taking apart his brain, basically. So kind of scary stuff, but hopefully it works, and we're crossing our fingers and whatnot. So I will be giving classes on Tuesday and Wednesday. It's unclear whether those will be on campus. They should be on campus. They might be virtual. That's what I'm working the details out of right now. They'll probably be on campus, though, because what's happening is it's a 2-phase surgery, and he gets probes implanted directly on his brain on Monday, and then we have to wait anywhere from 3 days to 2 weeks before the actual surgery takes place. So anyway, more information than you needed to know, but that's what's going on. We will not have class Monday, and I'll send out that information. I gotta go because someone is knocking on my door, and this video is done anyway, so we will talk to you later in the next class. Thanks.